As part of this meridional overturning circulation project that I got funded, we also looked at the boundary current, the Brazil current in the South Atlantic, and it's an important part of the MRC pathways. So, and we submitted a paper a while ago, and I'm just now revising it, so I have to resubmit tomorrow, and this is basically what's in that paper. I think everybody agrees we need good estimates of the boundary current transports to derive the meridional overturning circulation. And this objective of this study was to look a little bit how good can we do it with the Argo and SSH product. Observations in that area are not really covering good in space and time, so it's kind of poorly observed, especially if you compare it with what's available in North Atlantic. And so now we are looking at it using the new results, new estimates, and the earlier studies and model results to learn a little bit more about the Brazil current itself. So this is kind of a summary of earlier results which I showed previously. So it's mostly synoptic surveys, but there are two time series products that are also included in this plot. And we see the latitude dependence, simplified presentation of that is the red line. And then we see the large scatter on the confluence. It's nothing new really. And then we have a few, the green circle and the cyan circle that or ellipse that indicate some values that are a little bit more outlandish than the other values. So they're kind of out of the range where you would expect them, but I'm not really surprised about it because it's pretty tricky to get the Brazil current transport. And so sometimes you have strong eddies and then you can't really find it. So this is one early time series from 1993, which basically shows northward transports for short periods of time along the red line, but mostly it's southward, and there's some variability, mesoscale, time scales like 2 months or so. There also is a phase where one can see the Brazil current offshore. Well, I guess I have to take the mouse as a pointer. So here we have an offshore southward flow, and right onshore it's northward, so that the Brazil current just shifted offshore to the location here between 7 and 6 right here instead of 7 and 8. So very variable at 35 south, which is not really surprising. And this is another time series which is a little bit longer. And it shows pretty strong variability, and it's hard for me to see it from here. Anyway, so it shows some mesoscale variability. It shows some times with annual cycle, some years with semi-annual cycle. So it's a highly dynamic area. Here we also had some XPT sections where it's even harder to see what's annual, semi-annual, or mesoscale. But what I found interesting here, we have the 35 south, which is the red crosses in open circles, so that's these guys here. And then we have 24 south, which is the red dots. So you see there's a latitude dependence again that I talked about before. So this is the data coverage of the product we are currently using. So coverage with Argo profiles in the top, and coverage with velocities at the bottom. And there are fewer velocities, fewer floats, fewer velocities, because we are limited to the drift depths of 800 to 1100 decibars that we can use for the velocity. So the method I showed before, so basically from the previous time to now, we basically changed one thing only. So we still derive the dynamic height profiles from the temperature and salinity profiles. Then we do a correlation between sea surface height and dynamic height, which we formerly did with weekly Arizo fields, and now we do it with daily Arizo fields, which gives us better match-ups in the times between the profiles and the sea surface height. And the rest didn't change. We derived the fits needed to generate synthetic dynamic height fields. And then from that we get the monthly time series of those fields, and then we can estimate the geostrophic velocity and get the time series that way. And then that's basically a velocity field with respect to 1,000 meters or decibars. And then we get the subsurface velocity from the trajectories to do a geostrophic adjustment. And so that's shown here, how the 20-meter velocity changes, the top panels, the U and V, how it changes when you add the subsurface velocity shown in the second row for the zonal manual component from the trajectories. And then we get a total velocity as an adjusted geostrophic velocity, which then gets a nicer South Atlantic current down here. It gets a nicer Antarctic circumpolar current. The Agulhas current is stronger, so it improves a lot of things. It also makes the boundary current stronger, and the Brazil current becomes stronger, the Malvinas current becomes stronger and more pronounced. So it improves it a lot. And then to verify how well we are doing, we can compare it to independent velocities. So this is in comparison to surface drifters at 15 meters from the product that Rick Lumpkin puts together. And so we see that the drifters have a little bit higher velocities in areas where the velocity is relatively high. So the South Atlantic current seems to be a little bit stronger. Agulhas current is pretty good. The Malvinas current seems to be a little bit stronger, which partly at least that impression because it can show the on-the-shelf component that Argo cannot show. So I'm quite happy with this comparison. It's not quantitative, but qualitative I'm very happy. So this is similar, focusing now on the area of the Brazil current itself. And there's a vector plot, and then below is the dot plot. And to me, the main take-home message from this is that in the area where the Brazil current itself is, so where the velocities are higher than 15 centimeters per second, we get a relatively good match. So that's in these dot plots, that's the area down here, closer to the black line. So to the diagonal here. So the higher the velocities are, the better it seems to fit. So that's good for the boundary current. This is another way of looking at it as monthly means. So right at the boundary, we can see pretty good matches in most months here between the blue and the red line. And then a little bit of an exception over here in those 3 last months here where the drifters have higher velocities. But it's, yeah, you have the geostrophic component in the drifters, and Argo and SSH doesn't have it, so I'm not too concerned about it. This is another comparison I did using the Argo product for April 2007 and the AX18 line in the same month, which is only like a 1-week plot. And the Brazil current here looks pretty similar, even so one is a monthly average and the other one is basically a weekly or 6-day average. And then if we look at the models now going beyond the observation comparison, we see that NSAP is also pretty similar to Argo and SSH. Soda and HICOM have stronger velocities here in the boundary current. And we will see that later, and that's again at 35 south. Then I was also just trying to see how does it compare with satellite imagery versus the location of the Brazil current. And this little black dot that you can hardly see, which is pointed out over here, is basically the largest sea surface height gradient at this latitude. And I'm showing the same dot in all the other panels. And so we see a strong chlorophyll A gradient on the western side of the boundary current. Here we see the velocity from Argo at 15 meters. And here we see the sea surface temperature gradient, which is also strong. It's a little bit to the west of the Brazil current. So yeah, and the onshore component we can't measure with Argo. So that's so then this is the vector plot, again, climatology from Argo on the left, top left, from NCEP GODAS, from HICOM and from SODA. And in principle they show pretty similar, the boundary current. In Argo you see a little bit weaker, especially in the northern part. It's harder to find in the climatology because it's so variable. And then in SODA it seems to be very strong, and the confluence is quite a bit farther south than in the other products on the climatological average. Yeah, Brazil return current I wrote is visible in all panels, but I'm not going to deal with it here, so it's not that interesting. So this is the mean Brazil current transport, and to the north of 27 south I only took the transport in the upper 400 meters. Farther south I took the 800 meter layer thickness. And then it's Argo and SSH in black, and then NCEP is blue, dark blue, and has mostly a bit higher north of 30 south, and elsewhere it's very close to Argo and SSH. SODA is similar to NCEP in the north, but then in the south it gets a very large transport, which I think is one reason why the Brazil current goes so far south and the confluence is too far south. I'm looking forward to a SODA 3, and then maybe we can get something nicer. So this is SODA 2.26. Then HICOM is a little bit, sometimes matches Argo very well, sometimes a little bit higher, but in general I think it does a pretty good job when it comes to the mean. And so the left-hand side has the meridional component only, and the right-hand side has a full component, and I put them both here because the left-hand side with the gray symbols and dots with arrow bars shows the previous estimates from mostly synoptic sections. And these sections often go perpendicular across the Brazil current. So if you only look at the meridional component, they will have higher values, and that is confirmed here. On the right-hand side, they match a lot better than on the left-hand side. So doing the full transport does help with that agreement. Then I recalculated the latitude dependence. So between 20 and 25.5 south, more or less, the red line goes right through it, but you don't really have much of a slope, you have more of a scatter. So this time I estimated the mean for that latitude range and come up with 5.9 plus minus 3.5 square roots based on the previous estimates. And from the new product, if you take the meridional component, it's 2.4. If you take the shelf parallel component, you get 3.3, which is pretty close to previous estimates. Then I only estimated the slope between 27 and 32, which is the area with the largest slope. And the previous had a 1.61 square roots per degree. the meridional component has 1.79, and the total transport has 2.54 stratos per degree. So I have to look at that more closely, because the meridional transport matches the historical estimate better than the full transport. And then farther south, the previous estimates have a quite large scatter, and I get less of a scatter now with Argo and SSH, and a little bit smaller mean, both for the meridional component and for the full transport. So these are now the full time series, smoothed with a Butterworth filter to reduce the mesoscale signal and mainly focus on the annual cycle and interannual variability. And showing some of the previous results again. So Argo and SSH mostly has high transports in December to February. And some years also have a secondary high, and we will look at that variability a little bit more later. The models generally have mostly an annual cycle. And then the NCEP has a relatively large amplitude at 24 south, and the HICOM has a relatively large amplitude at 38 south, where the confluence is. SODA again also has a large amplitude at 24 south. And the other thing I notice is with NCEP, you do see a change in the first couple of years where it starts off quite far away from the Argo and SSH. And then it starts matching pretty good, starting in about 2004. And so I think that's because before data assimilation, before Argo had enough data to assimilate a lot of data in the South Atlantic, NCEP was having a hard time in getting the Brazil current transport right. And once Argo had enough data, it was doing a lot better. And the other models had a more realistic Brazil current from the get-go, seems like, so they didn't have that change. So here the top shows the mean annual cycle, and the bottom shows the annual cycle of the anomaly, so with the annual mean removed for each year. And in both ways of doing it, we get a pretty pronounced annual cycle, except at 24 south, where Argo has a pretty weak one, but after you remove the interannual variability, you also get a pretty pronounced annual cycle. And so it's the models mostly agree pretty well with the annual cycle. SODA has a little bit of an offset in terms of the timing of the annual cycle. And again, I'm looking forward to SODA 3, so that will be doing a lot better, I think. So then I look at how can I relate the Brazil current transports to ocean indices. Well, El Nino, there was nothing. So Nino 3, the AMO, there was nothing. And then the SAM had a little bit interesting stuff to see. So the small one is less interesting, but it's a 12-month Butterworth filter time series, both of the SAM and the Brazil current transport. And it shows correlations that are in the significant range, but it has some weird characteristics with terms of the lag, and the time series look pretty chaotic. And I smoothed it a little bit more using a 24-month filter to just focus purely on the longer term interannual, which is a little bit tricky because the time series is so short. It does seem to show robust correlations and a robust lag, not like the 12-month Butterworth filter. And at least especially at 24 south, where the influence of the confluence is not there, you see a trend from 2002 about until 2011, where both the SAM and the Brazil current transport increase. And then, so that I thought is pretty neat. And then I thought, well, let's look a little bit more at this. And that comes later. And then I did a coupled EOF. because SAM is kind of between the sea level pressure between 40 and 60 south, the gradient. So why would that drive the Brazil current? Well, because of what the sea level pressure at 40 south does. And in the top panel, we see the first mode of the coupled EOF, which explains 49% of the variance. And that mostly has a 2 to 4 year cycle. And it pretty much represents the subtropical gyre dynamics very well, I think, because it has the highest amplitudes in the eastward and westward currents of the subtropical gyre and the node in between. And then the second mode explains about 29% of the variance, and it has the node, so the zero line, a little bit farther south. It still has a quite strong signal at 40 south, which I think is what SAM captures. And in the time series below that panel, we see that there's a gradual increase in 2001 to 2008, which is almost the same period that the SAM showed that increase relationship to the Brazil current. So I think there is something to it, to that increase, and that it's actually just the sea level pressure and the corresponding changes in the wind field that drive this longer term trend. And now I'm getting into a lot of plots. So I did wavelet transforms at the 3 latitudes. And pretty much for the transport in the top panel, they all show, and I removed the mesoscale signal from these because they are very strong. So after removing the mesoscale, you basically see some signal at the semi-annual cycle and then some signal at the annual cycle. And in this case, the annual cycle is pretty strong for the transport. The middle panel will be the same in all 3 plots. So it has the SAM, it has both semi-annual and annual cycles, and it has something at a 2-year period, an interannual cycle, especially like around 2009 for about 2 years, so it has that signal. And then the bottom shows the cross wavelet, and it shows a little bit at 24 south, that there's a 24-month signal, but it's kind of only for a very short period of time. And as for the our transport, the annual cycle dominates in about 2005 to 2009. At 35 south, we get more semi-annual, less annual in the wavelet power spectrum. And then in the cross wavelet power spectrum, basically the 24 months is gone. The 12 months is only for a very short period of time. It's again mostly semi-annual. But on the climatological mean I showed before, it does have an annual cycle. Only in the wavelet it doesn't really show up that strongly. But it has the highest power in the annual cycle for a short period of time. At 38 south, it's similar. Again, there's a lot of semi-annual and some annual cycle in the transport. And the 24 months is a little bit stronger in the cross power spectrum, but it doesn't really reach significance, not quite. So it's getting more red, but it doesn't make it to the having a nice black lines encircling it. The black line is the 95% confidence, the thick black line. Then I get into conclusions, comparison with independent observations. So the climatological maps of surface drifter and Argo and SSH velocities agree pretty well when it comes to structure, representing the major features of the circulation. We do have differences in regions with very high energy currents and strong mesoscale variability, which is captured better by the drifters and often has a large geostrophic component, so that Argo and SSH geostrophic velocity can't capture. And it's not the Ekman velocity that's missing because I added that in the comparisons. Fortunately, in the Brazil current, the differences are really not that large except near the confluence. Then the monthly climatology of velocity at the western boundary is also pretty good at 35 south. And then the April 2007 comparison also shows quite good agreements with the XPT sections done in the same month and year. And the velocity field we are getting is at least not inconsistent with the satellite maps of sea surface temperature and chlorophyll A. Then we had the means in the northern part of the Brazil current, where we get a little bit lower values than the previous studies, but it's within the standard deviation envelopes. We get a similar slope for the meridional transport compared with previous estimates, but not for the full transport. We have a larger latitude dependence between 27 and 32 south. And then closer to the confluence, around 35 south, we get a little bit smaller transports, both for the meridional component and for the full component. But I don't really think that that difference is very significant, but we will see how it evolves over time. Then we compared models versus Argo and SSH, and so in general the three models have the same characteristics in the latitude dependence. NSEP GODAS is pretty close to Argo and SSH, also south of 30 south, where the other two models are more different, especially SODA has almost twice as high transports. And HICOM is in between NSEP GODAS and SODA, and it's relatively close to the observations, but it has higher transports. Then we have the meridional and the full transports have very similar characteristics. The latter follow the slope and have higher values, and they match the historical data better because they are often based on sections that are perpendicular to the Brazil current rather than zonally oriented. So then with the variability, most years have a high transport in December to February. The secondary highs occur often in June to September, for example in 2001, 2007, 2013. On the average we have an annual cycle, but at 24 south it's only prominent if I do an annual cycle of the anomaly, and it's relatively weak if I just take a monthly means to get the annual cycle. We found some relationship to SAM on interannual timescales with significant correlations and a lag between 0 and 1 month. So it would be nice to have a time series that's like 2 or 3 times as long, and you could look at it much better. Then we found the first couple of EOF explains 43% variance and has a periodicity of 2 to 4 years. And the second EOF had the gradual increase in 2001 to 2008 that supports the relationship between the Brazil current transport and the SAM I found in the strongly filtered time series. The wavelet transform supports the complicated nature of the variability with significant semi-annual and annual periods depending on the year and also the latitude. And the cross-wavelet transform again highlights that there's some relationship to SAM, but because of the shortness of the time series, it can't reflect the 2001 to 2008 slope. So but it showed something at the 24 months periodicity. So, and this is the end. Questions?